the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are just going through column space and null space. And now that you've gone through those, it's probably important for us to really compare and contrast those two sets. And remember, column spaces and null spaces are subspaces. The null space of a matrix, which is an m by n matrix, is going to be a subspace of Rn. The column space of A, where A is an m by n matrix, is going to be a subspace of Rm. So let's talk about each of these sets, or subspaces if you will, and we'll do it item by item here. So the null space of A, well, the null space, like I just said, is a subspace of Rn. The column space is a subspace of Rm. The null space of A is implicitly defined. That is, you are given only a condition, which is that Ax be 0, that the vectors in the null space of A must satisfy. The word implicitly here means it's not in your face what the null space is. You kind of have to find it. Versus the column space, that's actually explicitly defined. The column space, it's a span of the column vectors. And really the next item in this list, which by the way, I did not create this list, so please do not credit me. This is actually from the text that I used. I just love this list. This third item is kind of encapsulating what I just said, which is that it takes time to find the vectors in the null space of A. You basically have to solve Ax equals 0, so row operations on A0 are required. Versus the column space of A, well, that's pretty easy to find. The columns of A are displayed, all you have to do is create the span of those columns and you have the entire column space. So it's very easy to find the column space given a matrix, but not so easy when you're trying to find the null space. Another contrast between them, there's no obvious relation between the null space of A and the entries in A itself. So if I handed you a matrix A and said, hey, can you just tell me what the null space is by looking at this matrix? The answer is no. You have to solve Ax equals 0. And again, speaking of the column space of A, there is an obvious relation between the column space of A and the entries of A, since each column of A is in the column space of A. Item 5 in both lists here give us kind of the defining characteristics of being these subspaces. A typical vector is in the null space of A if it has the property that A times that vector is 0, versus a typical vector in the column space of A has the property that the equation Ax equals V is consistent. Notice in this case, a vector is in the null space of A if when you plug it into the left-hand side, in other words, A times that vector, if that becomes 0. And it's because the null space of A is all about inputs for our transformation. On the other hand, the column space of A is all about the outputs of our transformations. And so a vector is in the column space of A if it's an output or if it's in the range of our transformation. So it will be the right-hand side of this equation. All right, what else do we have here? Just 3 more to go. What if I just hand you a specific vector and I ask you, is that in the null space or the column space of A? This null space is pretty easy. You just multiply that vector against A. If it becomes 0, then you know that vector's in the null space of A. The column space, not so easy. The only way you can tell if V is in the column space of A is if there is a solution to Ax equals V. That is, you have to place V in an augmented matrix with A and solve. So there's a lot of work there. Let's take a look at step 7 or list item 7. And actually items 7 and 8 are going to add to our large table involving the invertible matrix theorem and the existence equivalence theorem and the uniqueness equivalence theorem. So let's see. Item 7. The null space of your matrix is 0 if and only if the equation Ax equals 0 has only the trivial solution. Remember, Ax equals 0 always has the trivial solution, but if it only has the trivial solution, then the only thing that solves it is 0. Thus, the null space of A has to be the 0 vector only. When it comes to the column space of A is the entire vector space it's contained with if and only if the equation AX equals B has a solution for every B in Rm. And that is a theorem we wrote down at the end of the last video. And in fact, item 7 on the null space side was another one that we had stated at the end of the last video. Finally, and this is kind of a result that we've seen in the past, the null space of A is just the 0 vector if and only if the linear transformation x to ax is 1-to-1. And the column space of A is the entire vector space Rm if and only if the linear transformation from x to ax maps Rn onto Rm. That should make sense. If you want to generate the entire column space, or I'm sorry, the entire vector space Rm, then your column space had better map all the way onto Rm. Now I did use alternating highlighting colors here, but actually I think what I'm going to do is re-highlight these for you in terms of ease of use. And you'll know what I mean when I get there. So for example, the null space of A is a subspace of Rn, and the call space of A is a subspace of Rm. There's not really one of those that's easier than the other. But the null space being implicitly defined means it's actually harder to define the null space of A given a matrix A than it is to define the column space of A given a matrix A, because the column space of A is explicitly defined. If I give you a matrix, you know the columns of that matrix generate or span the column space of A. So the column space is actually much easier to work with than the null space. So I highlight the column space green for being easier and the null space pink for being harder. Likewise, it takes time to find vectors in the null space of A because you have to do row operations on the augmented matrix A0. But it literally takes no time at all to find vectors in the column space of A because, well, the columns of A generate the entire space. Likewise, there's an obvious relation between the column space and the entries in A since each column of A is in the column space of A. And for the null space of A, there's just no real obvious relationship between entries in A or columns of A and the null space of A. So far it looks like the null space is always going to be the harder one to work with, but that's not the case. If I give you a single vector, determining whether or not that single vector is in the null space is actually pretty easy. Just multiply A times that vector. If it becomes 0, you're good. But again, given a single vector and asked is this in the column space of A, that's actually a little more work because you have to solve AX equals that vector. Likewise, again, given a single vector, it would take time to tell if that vector is in the column space of A because you have to perform row operations on this augmented matrix. But again, given a single vector, it's easy to tell if that vector is in the null space of A because all you have to do is multiply it by A to see if it becomes 0. So essentially, if you're given single vectors, null space is the winner as far as ease goes. But if you want to find an explicit description of the entire set, the column space is much easier to deal with. And I kind of wrote that down, kind of chicken scratch on the left-hand side, but there you go. So that's kind of a nice way to visualize this as well. Let's go ahead and see an example that involves this. Let our matrix A be this messiness right here. Find a K such that the null space of A is a subspace of RK. Now, this is not a use technically of that contrasting list that we've just gone through, but it is important to note. I just want to find the dimension of the null space of A. Like, what is the size of each vector in the null space of A? Now remember, the null space of A is actually a set of solutions to AX equals 0. And these solutions have to have the same dimension as the number of columns in A, because you're multiplying A by those vectors X. So in this case, K would have to be 3. So that the null space of A is a subspace of R cubed. Likewise, to find a K such that the column space of A is a subspace of RK, well remember, the column space is really the range of this equation right here. The set of all outputs is really what you want to think about. It's the range of the linear transformation. And all those outputs are in a space that matches the number of rows that A has. Well, A has 4 rows, so I know that K has to be 4. And by the way, state a non-zero vector in the column space of A. As I mentioned in the list previously, if we're looking to state a single vector, well, the column space is the harder question. However, that's only if somebody says, hey, is this vector in the column space of A? But if they just say, write a vector in the column space of A, that's actually not too bad. Remember, the column space of A is a span of the column vectors in A. So I can take a non-zero linear combination of those vectors. Let's just do 1, 1, 1. And that will imply that 5, -7, 2, 0 is in the column space of A. Notice I wasn't given a vector and asked, is this in the column space of A? Instead, I just said, what's a vector in the column space of A? That's actually an easy question to deal with. A much easier answer to that, honestly, is one vector that is in the column space of A is that vector right there. Another vector is this vector right here. Another vector is this vector right there. So I didn't actually have to take a linear combination of those. I could have just stolen one of those. All right, so I hope that the concept of null space and column space is slowly coming together. It doesn't actually come together until you start doing problems. So I highly encourage you to read through your textbook while you're watching these, not at the very same time, but before you watch this video or after you watch this video, read the relevant section in your textbook to kind of fill in the knowledge gaps, and then do a couple problems from the homework. All right, that's all I have for you here. There's going to be one more video in this series on null space and column space, and that involves definitions for linear transformations. I hope to see you there. Have a wonderful day. Be a wonderful human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.